Okay, so what about real gases, right? We talk, about the ideal gas law, and talk about ideal this, ideal that. Ideal things are great, but, sometimes you have to deal with real. So let's remind ourselves what we mean by an ideal gas. In an ideal gas, there are no attractions between the gas particles. They bump into each other, completely elastic collisions, and the ideal gas molecules have negligible volume. The volume doesn't matter. So at reasonable temperatures and pressures, like STP, real gases behave very much like ideal gases. Not exactly, but pretty close. So if we look at molar volume, the molar volume of an ideal gas, 22.41 liters for 1 mole. And here are several real gases and their molar volumes. 22.06, so that's a little low. 22.31, a little low. Ammonia is really, really close, and so is nitrogen. Helium nails it, and hydrogen's only a teeny tiny bit higher. So these molar volumes are extremely close to ideal at STP. But if we go to high pressure or low temperatures, then the real gases don't behave ideally anymore. So at low pressures, the molar volume of argon is nearly identical to that of an ideal gas. But if we increase the pressure, so we push down on this, increase the pressure, that's decreasing the volume. Now these particles are very crowded together, aren't they? As we get them closer and closer together, the molar volume becomes larger than that of an ideal gas. Because at high pressures, the large size of these argon atoms begins to become significant. It's not so small that you can just ignore it anymore. So you take the people in Wyoming and you crowd them together, and you bring them closer and closer together, and after a while it's going to start to matter if they're all 300 pounds or they're all 98-pound weaklings, right? When they're all spread out and there's lots of space, it doesn't matter. But at very high pressures, we're crowding the particles together, and now the size of the particles comes into effect. Real molecules do take up space. We don't observe this, though, until we get to high pressures. So here we have a graph of molar volume versus pressure in atmospheres. And we see at low pressures, this is 200 atmospheres. That is crazy high pressure. So anything we could do in this lab, we'd be well within this range of reasonable pressure where molar volume is ideal. But when we increase the pressure, what we see is that argon's molar volume is higher than predicted by the ideal gas law. So as you increase the pressure, we get some deviation. So this was observed, that real gases deviate. So van der Waals, back in 1873, made a modification of the ideal gas law to fit the behavior of real gases at high pressures. So at high pressures, the volume goes up, and so he adds a factor in here, NB. So N is the amount of gas in moles, and B is a factor. It's called the van der Waals constant. It's different for every gas because each different gas has molecules that are different sizes. And that value of that is determined experimentally. You need to use this modified version if you're working at really, really high pressures. And we have this constant, and we can account for the difference from the ideal gas behavior. Well, another thing that can happen that will cause deviation is low temperatures. So at high temperatures, we see real gases and ideal gases behaving very similarly. But at low temperatures, we observe that the pressure of the gas is lower than would be predicted by the ideal gas law. And what's happening here is the ideal gas law says that the particles do not interact at all. As you go to Lower temperatures, what happens to the velocity of the particles? They slow down. So now the particles are still moving around, they're bumping into each other, but now when they bump into each other, they're at slower speeds. Real molecules, real atoms, do have some attraction for each other. When the speed gets lower, now as those two particles come together and bounce off of each other, they may stop for a chat. They're like, hey, hi, how are you? And it slows down the collision. And so that affects the behavior of the gas. At low temperatures, we get interactions. They spend more time interacting. They'll interact with each other. And so that causes them to collide less with the walls, and the pressure becomes less than we would expect. So van der Waals also modified the ideal gas law for this. You need to use this at low temperatures. Pressure would be less, so you're going to subtract this term. And again, A is this van der Waals constant for pressure, and that's going to be different for each gas. So here we see the pressure versus temperature in kelvins for an ideal gas in the red and xenon in the green. And room temperature is about 273, so that's down here. So at room temperature, there is deviation due to the interaction of the particles. So the pressures are not going to be exactly what we expect.
If pressure is changing at room temperature a lot, why is there a standard pressure against 2 people?
Well, that's just to provide a reference point. So here, the pressure is changing because we've got a particular amount of gas and we're holding the volume constant. We're changing the temperature. And so the pressure has to change. Standard temperature, standard pressure is just a reference point that we've agreed. That's what we're going to compare to. So you can combine these two modifications into one. It's called the van der Waals equation. The good news is you don't need to know this one because that's a mess, isn't it? The good thing about that is it makes PV equals nRT seem pretty simple. So here's the correction for intermolecular forces. Here's the correction for particle volume. And this is what's used for real gases. Here's some of the constants for different gases. There could be like a homework problem or something that's going to ask you to do this, but this will not be on an exam. I want you to be aware of it, though. You should know that real gases deviate from ideal behavior when the pressure is high and when the temperature is low.
So that's the equation for when the temperature is lower?
This one will account for both. It'll account for both. If we graph PV over nRT. So this PV over nRT should equal what? N, right? Amount of gas in moles. If we graph that versus pressure in atmospheres for 1 mole of a gas, ideal behavior, this should be the same at all pressures. It should be 1. That's what the ideal gas law tells us. And here is the behavior for some real gases. Helium, just nice straight line going up. Water dips way down here and then begins to come back up. What we see is the difference. There's 2 things that are affecting deviation. One is particle size, and the other is interactions between the particles. So for helium, for neon, and for argon, it's the particle size that's causing deviation. Xenon kind of goes both ways. Initially, it's interactions. And for water, it's all about the interactions. Water has a lot of interactions between the molecules. So you get that down to a lower temperature and well, it condenses is what it does. So for xenon, at these lower pressures, it's the interaction that's important, but at higher pressures, it's the volume of the particle that's important.